Good morning, students. In the previous lecture, we discussed resolvents and Laplace transform. And in today's class, we will derive the solution of wave equation from the solution of heat equation by applying the same Laplace transform. So let us consider the wave equation given by second order partial derivative of u with respect to t minus Laplacian of u is equal to 0 in Rn cross open interval 0 to infinity. Rn is n-dimensional real Euclidean space with the two initial conditions. First initial condition when the time is 0 is that the value of function u is g, and second initial condition when the time is 0 is that partial derivative of u with respect to t is 0. We have to find the solution for this initial value problem. Here n is odd, this g is a known smooth function having compact support. Let us take u is a bounded solution of this problem. We extend the function u to the negative term by defining u at xt is equal to u at x comma minus t if t is negative and x belongs to n-dimensional real Euclidean space. Then we can say that the partial differential equation for wave equation, which is utt minus del u is equal to 0. This denotes second order partial derivative of u with respect to t. Now this equation is satisfied in the Cartesian product of Rn with R. R is a set of real numbers. Now let us define a function v, which is the function of x and t, defined by 1 upon 4 pi t whole raised to the power n by 2 integral minus infinity to infinity e raised to the power minus s square upon 4t into u at the point x comma s. Now let us find the Laplacian of this function with respect to the space variable x. On the right side, only this u is a function of x. So if we apply Laplacian on both sides in this equation, the right side becomes 1 upon 4 pi t whole raised to the power n by 2 integral minus infinity to infinity for the function e raised to the power minus s square upon 4t into Laplacian of u at the point x comma s. Now let us substitute the value of Laplacian of u at the point x comma s, because u is the bounded solution for this partial differential equation. So the value of Laplacian of u at the point x comma s, that will be second order partial derivative of u with respect to s at the point x comma s. So we have substituted the value of this term here. Now we can find the value of this integral by using integration by parts. Let us consider this term as first function and this is second function. So by integration by parts, this will become 1 upon 4 pi t whole raised to the power n by 2 into this first function as it is. Integration of this term is curl u by curl s between the limits minus infinity to infinity minus integral derivative of this term into integration of curl to u by curl s2. Derivative of this term is given by e raised to the power minus s square upon 4t into minus 2s by 4t. So this is the partial derivative of this term with respect to s into integration of this term, that will be curl u by curl s. Now if we substitute these limits here, this term will become 0. So finally the Laplacian of the function v with respect to the space variable x, that becomes 1 upon 4 pi t whole raised to the power n by 2 into 1 upon 2t into integral minus infinity to infinity s e raised to the power minus s square by 4t into partial derivative of u with respect to s at the point x comma s. Now again using integration by parts formula to evaluate the value of this integral. These two terms we have taken as it is here by using integration by parts. First function as it is, integration of curl u by curl s with respect to s, that will be u. This expression between the limits minus infinity to infinity minus integral derivative of first by using product rule and integration of this term. Now derivative of this term, that will be by product rule as it is, derivative of e raised to the power minus s square by 4t, that will be e raised to the power minus s square by 4t into minus 2s by 4t plus this function as it is, derivative of s with respect to s, that is 1. Integration of this term with respect to s, that will be u. Now if we substitute these limits, this expression will again become 0. So we are left with Laplacian of v is equal to 1 upon 4 pi t whole raised to the power n by 2 into 1 by 2t into integral minus infinity to infinity 2s square upon 4t minus 1 into e raised to the power minus s square by 4t into u. This integral is with respect to s. Now this can further be written by taking 1 upon 2t inside the integral and multiplying with these two terms. So finally Laplacian of v with respect to x becomes 1 upon 4 pi t whole raised to the power n by 2 into integral minus infinity to infinity of the expression s square upon 4t square minus 1 upon 2t into e raised to the power minus s square by 4t into u at the point x comma s. This is the value for Laplacian of v with respect to x. Now let us find the partial derivative of v with respect to t. From the equation second, differentiating with respect to t partially. So this will become vt means derivative of v with respect to t, and on the right side by using product rule, first function as it is, derivative of this term with respect to t, that is minus infinity to infinity e raised to the power minus s square by 4t into the derivative of this term partially with respect to t, that will be s square upon 4t square. This term as it is because it is not a function of t. Then plus second term as it is, derivative of this term, that will be given by 1 upon 4 pi whole raised to the power n by 2 into minus n by 2 into 1 upon t raised to the power n upon 2 plus 1. Putting n is equal to 1 here, and also in the equation 3 we can see that Laplacian of function v with respect to x, that is same as the partial derivative of v with respect to t. It means the function v satisfies the heat equation, and also the initial condition as t approaches to 0, the limit of the function v, that is g, because we are given in the statement that at t is equal to 0 the value of function u is g. So finally we can say that the function v defined by the equation 2, that is a solution for the heat equation. And also in the second section we already derived the fundamental solution for heat equation, and it is given by v as a function of x and t, defined to be 1 upon 4 pi t whole raised to the power n by 2 into integral over Rn of the function e raised to the power minus x minus y mod square upon 4t into g at y. Now we can compare the two values of the function v from the equation 2 and equation 7. So finally we get the expression 1 upon 4 pi t whole raised to the power n by 2 into integral minus infinity to infinity e raised to the power minus s square upon 4t into u at the point x comma s is equal to 1 upon 4 pi t whole raised to the power n by 2 into integral over Rn for the function e raised to the power minus x minus y mod square upon 4t into g at y. Now in this equation let us put lambda is equal to 1 upon 4t. After putting lambda is equal to 1 upon 4t, now on the left hand side we can see that the expression under this integral sign, this is an even function. So the integral from minus infinity to infinity, that will become 2 times integral from 0 to infinity. So finally this equation can be written as 2 times integral 0 to infinity e raised to the power minus s square lambda into u at the point xs is equal to integral over Rn e raised to the power minus x minus y mod square into lambda into g at y. Now let us use the theorem for polar coordinates to find the value of this integral. According to the theorem of polar coordinates, if we have a function which is defined on n-dimensional real Euclidean space and is a real valued function, then we can convert the integral of this function from Rn into an integral over a sphere having the center x. So using the theorem, the value of this integral of the function f over n-dimensional real Euclidean space, that is given by integral 0 to infinity into integral over the sphere with center x, radius s. Integral of this integral is with respect to s, and this is the integral of function f, and this integral is with respect to the variable r. Now using this formula for this integral, this equation can be written as integral 0 to infinity e raised to the power minus s square lambda into u at the point x comma s is equal to half of the integral from 0 to infinity of integral over the sphere with center x, radius s, e raised to the power minus x minus y mod square into lambda into g at y ds dr. Solving this equation, we can find the value of this function u, and this function u that gives us the required solution for the given wave equation. So in this way, by using Laplace transforms, we can find the solution of wave equation, which is based upon heat equation.